Hello and welcome to the Reigate College Maths Further Mechanics 1 video on conservation of momentum. So today we're looking at the principle of conservation of momentum. And that principle states that if two objects are moving in a straight line and they collide, then the total momentum before the collision is equal to the total momentum after the collision. This is called the principle of conservation of momentum, and when you're working on momentum questions, if you write PCOM in your margin, then that makes it very clear that that is what you're doing. That's the standard abbreviation used in mark schemes. Before we move on to the questions in the booklet, let's have a think about what happens when two particles collide. So if I've got two particles, here and here, this one moving with a speed of 8, this one moving with a speed of 6, and notice that this one must be going more slowly than this one, otherwise this one won't collide with it. Then afterwards there are various different options, things that can happen. First of all, they could both continue moving in that positive direction. However, if this mass here is quite large, that might make this first mass reverse its direction. Another situation that you're sometimes given is that the first particle is moving and the second particle is stationary. When this happens, there are three options. So both particles might move in the positive direction. This particle may stop and this one will move in this direction. Or if this mass was large, depending on the velocity here, then you might have this second particle moving this way and the first one being reversed. So there are three options here that you might need to consider. You can also have two particles moving towards each other. If two particles are moving towards each other, then it depends on the relative masses and velocities, but they could, this one here could have its direction reversed, this one carries on, or they could both have their direction reversed. Possible that they could both travel in the negative direction after a collision as well. So you've got various different options. You need to consider what's going to happen there. Let's now look at some questions. As with the momentum questions we did in the first video, what's really important here is that you think about the direction that the particles are travelling in. So this question, we've got two particles A and B, of masses 2 kilograms and 4 kilograms, and they're moving towards each other. Take some time to read the question, make sure you know what's happening. They're moving towards each other on the same straight line on a smooth horizontal surface with speeds of 3 and 2 respectively. Now when I tackle these questions, I like to draw a before and after diagram. So I'm going to do that in these questions. Some people draw the diagrams like this, where you have the before above the particles and the after below the particles. I prefer to do two separate diagrams like this. So we've got this situation here. This is 2 kilograms, this is 4 kilograms. And we're told that the direction of A is reversed. So this is the particle A. So A is reversed, and it now is going in that direction with a speed of 2, and we want to find the speed and direction of B. If you are not told the direction of a particle, I would always put it moving in the positive direction and label it V. If it turns out it was moving in the other direction, your answer will come out as negative, and then you can just indicate that in your answer. So the first thing we're going to do is apply the principle of conservation of momentum. So that's when I write principle of conservation of momentum. And in order to do this, we need to say the momentum before the collision is equal to the momentum after the collision. So I've got 3 multiplied by 2 for the momentum of A. Now, this particle is moving in a negative direction, so I've got minus 2 times 4. That's the momentum of B, and that is equal to the momentum afterwards. So I've now got minus 2 times 2, this is moving in a negative direction, plus 4B. So this gives me 6, take away 8 is minus 2, is equal to minus 4 plus 4B. So I've got that's minus 2 there. So adding 4 to both sides, I get 2 is equal to 4V. So V is equal to 0.5 meters per second. And it's moving in the same direction as A was at the start. So make it clear in your answer which direction it's moving in. Part B, we need to find the magnitude of the impulse given by A to B in the collision. Now remember that the impulse given by A to B will be equal and opposite to the impulse given by B to A. So I'm going to find the change in momentum of A, because impulse is change in momentum. Impulse equals change in momentum. The reason I'm going to look at A is that I'm actually given both the values for A, so I know these values are correct. I've found this value of B, it's just possible I've got it wrong, and in that case I want to make sure I'm using values that I know to be correct. So the impulse is the change in momentum, which is the final momentum, minus 2 multiplied by 2, take away the initial momentum, 2 times 3, and that gives me an answer of minus 10 Newton seconds. So the impulse, we're only asked for the magnitude of the impulse. The impulse of B on A is 10 Newton seconds in this direction. So the impulse of A on B is going to be 10 Newton seconds in the other direction, but we're only asked for the magnitude. So all we need to say is the impulse is 10 Newton seconds. So in this question, we have a particle of mass 3 kilograms moving with a speed of 4.8 meters per second on a smooth horizontal plane. It collides with another particle, mass 1.5 kilograms, which is at rest. After the collision, the two particles coalesce. This means they join together and move as one particle. So let's draw a before and after diagram. So this has a mass of 3, and this has a mass of 1.5. The first particle moves with a speed of 4.8, the second particle is at rest. Afterwards, the combined particle which has a mass of 4.5, moves with a speed of v. So we're going to apply the principle of conservation of momentum, and we're going to say 4.8 multiplied by 3 plus 0, because no momentum, is equal to 4.5 multiplied by v, and that gives me that v is 3.2 meters per second. Part B asks for the magnitude of impulse in the collision. So we need to consider one or other of the particles. We may as well use the second particle because that has no momentum at the beginning. So that makes the calculation very slightly easier. So the impulse is the change in momentum. So for the 1.5 kilogram mass, we've got 1.5 multiplied by 3.2 is the momentum afterwards, minus 0, and that gives me 4.8 Newton seconds for the impulse. Final question involves two particles attached by a light inextensible string, and the string is slack to start off with. So when I draw these diagrams, I draw a slack string between them to start off with, and then I draw my after diagram just as the string goes taut. This is 2 kilograms and that's 8 kilograms. So we're told that they're at rest. P is projected away from Q. So this is P, it's projected away from Q with a speed of 4. And we need to find the common speed. So as the string goes taut, both particles will move with the same speed. A little bit like in the previous question when the particles coalesce. So principle of conservation of momentum tells us that 0 times 2 plus 4 times 8 is equal to 2v plus 8v. So this gives me 32 is 10v, so v is 3.2 meters per second. The magnitude of the impulse transmitted through the string when it goes taut. Again, we're going to say impulse is change in momentum. We'll consider particle Q. So if we do that, the momentum afterwards, the final momentum, is 2 multiplied by 3.2. The initial momentum is 0, so that is 6.4 Newton seconds.